Welcome to the lecture series on numerical methods, and currently we are discussing interpolation. In the interpolation section we have covered this finite difference approximations like Newton's forward difference approximations, backward difference approximations, and all of these finite difference operators. Today we will discuss about Lagrange interpolation method and Newton's divided difference interpolation. So first we will start about Lagrange interpolation formula. In the Lagrange interpolation formula is applicable for both these uniformly and non-uniformly spaced grid sizes. Especially in a interpolation formula, we will have these tabular values like x0, y0, x1, y1, x2, y2, x3, y3. So likewise. So earlier whatever this formula we have discussed or derived, basically all these lectures they are discussed for this finite difference operators which are used for equispaced points. Sometimes if you will just see these points which are placed here, like if you will have the tabular points like xi, yi, where I is varying from 0 to n here, then these points will be placed like x0, y0, x1, y1, x2, y2 up to xn, yn here. So if you will just consider these tabular points like x0, y0 will be placed like this point here, x1, y1 will be placed here, and suppose the next tabular point x2, y2 is placed here. Next the tabular point will be placed as x3, y3 here. So likewise suppose the points will be placed. But if you will just see the distance between these 2 points which are unequally, since this is not equals to this one or this is not equals to this one here. This means that we can just say that x1 minus x0 is not equals to x2 minus x1 here, or this is not equals to x3 minus x2 here. So in this case we cannot use like Newton's forward formula or Newton's backward difference formula or any of these forward difference approximations. So for that we need a separate formula which can deal this unequally spaced points here. So basically these unequally spaced points, here we will just consider 3 different interpolation methods to approximate this function with a polynomial. That is, first one is Lagrange interpolation method, second one is a Newton's divided difference formula, and third one is a Hermite's interpolation method. And in this method if you will just see, this method simply suggests to represent the given data like xi, ya, I equals to 0, 1, 2 up to n, which can be approximated in the form of yi equals to p of xi here, where p of x can be written in the form of a0, a1x, a2 x square up to an x to the power n, where these coefficients a0, a1, a2 up to an are to be determined. And to determine this n plus 1 coefficients here, since it is a polynomial of degree n, so we need like n plus 1 equations to evaluate these coefficients there. Since all of these are constants, all of these constants here, so one value like a0 can be taken to the right hand side, all of these variables associated here a1 to an can be evaluated by considering n equations here. So for that, suppose we have to consider a polynomial of degree 1 for the first case. If you will just consider the polynomial of degree n equals to 1 here, we can just write here the points like x0 and x1 with a linear polynomial approximation or a polynomial of degree 1 here, or polynomial of degree 1 here. That is p of x equals to f of x here, which can be written in the form like a1x plus a0. And if we will just approximate this function with a polynomial to determine these coefficients a0 and a1. From this equation we have to consider three equations, that is in the form of like a p of x. Then if you will just put that x equals to x0, where p of x is exactly equals to f of x, or at x equals to x1 suppose p of x is exactly equals to f of x here, then we can just eliminate these coefficients a0 and a1 in a polynomial form here. So if you just do the things, we can just write p of x equals to a1x plus a0, where a0 and a1 are the arbitrary constants which satisfies the interpolating conditions, that is f of x0 equals to p of x0 as a1 x0 plus a0 here. Similarly, we can just write f of x1, that is p of x1, this equals to a1 x1 plus a0, and our original form of the equation, that is especially written in the form of p of x equals to a1 x plus a0 here. So if we want to eliminate a0 and a1 from these three equations, we can just write these equations in the form like p of x x1, then f of x0 x0 1, f of x1 x1 1, this equals to 0. If you will just expand this determinant here, we can just obtain that p of x into x0 minus x1 minus f of x0 into, if you will just see, that is x minus x1 plus f of x1 into x minus x0 here, this equals to 0. If we want to find p of x, or the polynomial to be determined here, so then it can be written as p of x equals to x minus x1 divided by x0 minus x1 f of x0 minus x minus x0 divided by x0 minus x1 f of x1, which can be written as x minus x1 by x0 minus x1 f of x0 plus x minus x0 by x1 minus x0 f of x1 here. Since I have just minus sign is there, so I have just taken common minus from this denominator side. So that can be written in the form of x minus x0 by x1 minus x0 into f of x1, where I can just write this one as L0 of x f of x0 plus L1 of x f of x1 here, where I can just write L0x equals to x minus x1 divided by x0 minus x1, and L1x, that can be written as x minus x0 by x1 minus x0 here. So if we will just see here that these are called L0x and L1x are called Lagrange's fundamental polynomials, which satisfies, if you will just add it up both these terms here, like L0x plus L1x here, which can be written as x minus x1 by x0 minus x1 plus x minus x0 by x1 minus x0 here. So this total value can give you the values as 1 here. Since if we can just put here, that is L0 of x0, that is nothing but 1 here, since x0 can be replaced here. So x0 minus x1 by x0 minus x1, that will just give you 1 here. If I will just replace x by x1 here, this means that L1 of x1, that will just give you x1 minus x0 by x1 minus x0 as the value is 1 here. This means that Li of xj, this equals to 1 whenever I equals to j, and this equals to 0 whenever I is not equals to j there. then we can just write Li of xj, this equals to delta, that is Kronecker delta of ij, this equals to 1 if I equals to j and 0 if I is not equals to j there. So, if you will just extend this linear polynomial to another polynomial here, so we can just write this complete polynomial p of x as p of x equals to L0x f of x0 plus L1x f of x1 plus up to ln x f of xn, where this coefficient like Lix can be written as x minus xi, sorry, x minus x0, x minus x1 to x minus xi minus 1, x minus xi plus 1 up to x minus xn divided by xi minus x0, xi minus x1 up to xi minus xi minus 1, xi minus xi plus 1 up to xi minus xn here. And it can be written in a combined form, that is p of x, this equals to summation of I equals to 0 to n Lix f of xi here. And obviously this Lix will satisfy the property, that is Li of xj, this equals to 1 when I equals to j and 0 when I is not equals to j here. If I will just take the product of the term like x minus xi in the upper side here, so I can just write that one as product of summation I equals to 0 to n x minus xi divided by x minus xi here into your products like xi minus x0, xi minus xi minus 1, xi minus xi plus 1 up to xi minus xn here. And also sometimes people are just using, since this is a product form here, I can just write this one as product of I equals to 0 to n here, that is x minus xi divided by x minus xi into this term I can just replace as pi dash of I equals to 0 to n xi minus, or I can just write this one as, since these terms are written as xi minus x0, xi minus x1. So, if I will just take the derivative of this term with respect to xi here, then I can just write pi dash of xi here, that one. So, we can just denote in our like convenient form, that is in a derivative form, if I will just take the expansion here and with respect to xi, if I will just take the derivatives, then only this xi term except this xi term, all other terms will be 0. So, in that way also I can just write this expansion, that is in the form of like a xi minus xj if I will just write, or I can just write this one as x minus xi also. So, it is very convenient to express this Lix term in different senses, since all of these terms are occurring in the form of product terms here. So, that can be expressed. To go for this polynomials, what is just created in the form of like Lagrange interpolation. So, we will just discuss about a example, that using suppose like the data like x equals to 0, 1, 4, 5 and the corresponding data of y equals to 8, 11, 68, 123, how we can determine the value of y or the function f of x at the point 2, that we will discuss using Lagrange interpolation polynomial here. Since the data points whatever it is just given, it is given in the form like x as 0, 1, 4, 5 here, and corresponding y datas that is given as 8, 11, 68, 123. And since we will have these points like 0, 1, 2, 3. So, we can just go up to a polynomial that is of degree like 3 here. So, that is why we can just write this one as, or this Lagrange polynomial expression will be or the Lagrange polynomial expression is like Li of x. I can just write x minus xi, sorry, this is x minus x0, x minus x1 up to x minus xn divided by xi minus x0, xi minus x1 up to xi minus xn here. And the complete polynomial p of x can be written as L0x f of x0, L1x f of x1, L2x f of x2, L3x f of x3. So, if I will just go for the computation of L0x here, so L0x can be written as x minus x1, x minus x2, x minus x3 divided by x0 minus x1, x0 minus x2, x0 minus x3 here. Since we have here 4 data points, like the 4 data points can be signified as x0 equals to 0 here, x1 equals to 1 here, x2 equals to 4 here, and x3 can be written as 5 here. So, if you just put all these points here, that can be written in the form like x minus 1, x minus 4, x minus 5 divided by 0 minus 1, 0 minus 4, 0 minus 5 here. So, if we want to evaluate L0x at the point 2, since the question is asked to evaluate the functional value at point 2. So, directly we can just replace here L0 at the point 2 and putting this 2 at the position of x in each of this expression here. So, if you will just replace here like L0 of 2, so we can just write this one as 2 minus 1, 2 minus 4, 2 minus 5 divided by 0 minus 1, that is minus 1, then minus 4, then minus 5 here. And similarly, we can just write L1x also and L2x, then L3x we can just write, and if we just put all these values with the functional values here, we can just obtain the total expression as your y of x or p of x can be expressed as x minus x1, x minus x2, x minus x3 divided by your value, that is 0 minus 1, 0 minus 4, 0 minus 5 into first value, that is your functional value. I can just write that one as since it is just given as 8 here, plus x minus 0, x minus 4, x minus 5 divided by 1 minus 0, 1 minus 4, 1 minus 5 into 11 plus x minus 0, x minus 1, x minus 5 divided by 4 minus 0, 4 minus 1, 4 minus 5 into 68 plus x minus 0, x minus 1, x minus 4 divided by 5 minus 0, 5 minus 1, 5 minus 4 into 123. Since we want to evaluate this y of x or p of x value at exactly x equals to 2 here, so we can just put here y of 2, and this total value that can become as, or we can just obtain that value as 18 here. So, since we are just using this Lagrange interpolation polynomial, if you will just see the data points here, first point is 0, then second point is 1, then third point is 4 here. If you will just see this difference or this difference, both are unequal here, and again this 4 and 5, this difference is 1 here, this difference is 3, and this is 1 again. So, that is why you cannot use any class of like finite difference operators to find this value at x equals to 2 here. So, Lagrange method, this can also be applicable if we will have this data points is given, and if it is asked to evaluate these functional values within any of these functional values here. And for that, what we will do is that we have to fit another polynomial, suppose q of y, such that the function is defined as x as a function of y there. This means that always we are just expressing y as a function of x. If it is asked to evaluate this functional value, we can just use it in a reverse form. That means that we can just use that one as x equals to q of y there, since y as the independent variable and x as the dependent variable. So, for that we can just consider another example, suppose y equals to f of x, then usually we can just express in a inverse form here x equals to g of y here to find these values at the tabular points if a function is prescribed to us. The following data are prescribed here, like y equals to x q is given here, x at the points like 1, 2, 3, and y values are given as 1, 8 and 27 here, and the question is asked to compute the root of 21 from the above data using Lagrange's method, and also discuss the error associated in that formulation. So, for that what we will do is we can just express this function in a inverse way as like x is given here as 1, 2, 3, and corresponding y values that are written as here 1, 8, 27 here. And so, if the question is asked to find the value of x where y value is 21 here, we can just write this formulation in a reverse form, that x as a function of y here, especially if you will just see this part here, x is expressed as a function of y here. So, that is why we can just write this formulation x as a function of y, which can be expressed as y minus y1, y minus y2 divided by, we can just write as y0 minus y1, y0 minus y2, and corresponding value it will just take these values as x0 here, plus we can just write y minus y0, y minus y2 divided by your values like y1 minus y0, y1 minus y2 into this functional values, which can be in a inverse form, it can be written as x1 here, and the last part you can just write this one as y minus y0, y minus y1 divided by y2 minus y0, y2 minus y1 into x2 here. So, if you will just represent this Lagrange polynomial in this form here, so especially we are just writing in this form here x0 as 1, x1 as 2, x2 as 3 here, and corresponding y values, these are expressed as y0 equals to 1 here, y1 as 8 here, y2 as 27 here. And if you will just put these values here, then we can just find this functional values as like x of 21. Since the y value, it is asked to compute the x position, that where we can just find this cube root of 21 there. Since especially the function is defined in the form of like y equals to x cube here. So that is why if in inverse form, if you will just write, x can be expressed as y to the power 1 by 3 here. So that is why if it is asked to compute this one x of 21 here, so then we can just write this one as 12, sorry, this is like 21 minus your y1, that is here as like 8, 21 minus 27 divided by the corresponding values of y0 here as 1 minus 8, 1 minus 27 into x0 value is especially 1 here, plus if you will just write again like 21 minus y0, so y0 is a 1 here, then into 21 minus y2 here, so y2 is obviously, sorry, this is y2 is 27 here, this divided by like if you will just write here our value y1 means this is 8 minus 1, then 8 minus 27, and the second value if you will just write, this is 2 here, plus the third value if you will just write here, that is in the form of like if you will just see, so last value we can just write 21 minus y0, 1, 21 minus 8 divided by, if you will just see here, so especially y2 means this is a 27 minus 1, 27 minus 8 into the last value, that is given as a 3 here. If you will just go for this computation, so then we can just find this value in a particular form, and we can just obtain this value of x of 21 there itself. So if we will go for this error computation here, we can just find the exact cube root of 21 as 2.7589, and if we want to go for the computation of error terms here in case of Lagrange interpolation polynomial, that the generalized interpolating polynomial errors what is occurring in our finite difference operator, the same we can just find this error term, that in a generalized form we have just obtained that one as r of x equals to x minus x0, x minus x1 to x minus xn, f to the power n plus 1 zeta by n plus 1 factorial, where zeta should be lies between x0 to xn. So the same approximation we can just use over here also. For n terms, usually we are just writing this error term r of x as x minus x0, x minus x1 up to x minus xn, f to the power n plus 1 zeta by n plus 1 factorial, where zeta should be lies between x0 to xn here. So the same approximation we can just use for the computation of error here also, and in this case if you will just go for this error computation, I can just write r of x equals to x minus 1, x minus 8, x minus 27 into f triple dash of zeta by 3 factorial here. Since we will have here like 3 points, like n equals to 2 here, so 3 points, that is why we are just considering 1, 8, 27. So it can just generate a polynomial of degree 2, and that is why 3 points means we will have a polynomial of degree, suppose if we are just considering a polynomial of degree n plus n there, then we will have exactly n plus 1 terms. So that is why here we will have like 3 points 1, 2 and 3 we are just considering, that is why this degree of the polynomial will be 2 here, and if n equals to 2 here, obviously we can just write f to the power n plus 1, that is 2 plus 1 is 3 here. So, this represents the third order derivative here, and this is 3 factorial. So, if you will just go for the computation of this error term here, so y can be expressed as in the form of like x to the power 1 by 3 here, and if you will just go for this triple order derivative f triple dash of x here, I can just express this one as 10 by 27 x to the power minus 8 by 3, and the maximum value of f triple dash x at x equals to 1 it can just obtain, and hence your error term, that is r of 21, can be written as 21 minus 1 into 21 minus 8 into 21 minus 27, and the maximum value that is occurring at 10 by 27. So, that is why 3 factorial I can just write this one, that is as r of 21 as 21 minus 1, 21 minus 8, 21 minus 27 into this one as 10 by 27 into 1 by 6 here. So, this total value it is just coming as 96.3 here, or 96.29 something, it is just coming over that. So, the drawback of this method, that is if we want to add suppose any other term, we have to go for this computation of n plus 1 terms here. This means that whenever we have an extra point here, usually we are just writing p of x as f of x, or we are just writing this one as y of x here, that is represented in the form of L0x f of x0, L1x f of x1. So, likewise we are just writing ln x f of xn here. But suddenly if suppose one extra point if we want to add it up here, then we have to consider that this n plus 1 point in each of these products here, since L0x is usually expressed in the form of x minus x1 to x minus xn by x0 minus x1 to x0 minus xn there. So, if another extra point if it will be added, so in upper side also we have to consider like x minus xn plus 1, lower side also we have to consider x0 minus xn plus 1 also. So, in each of the terms if it is multiplied, so a large multipliers it is required to go for the solution process. In this Lagrangian method, usually if you want to add suppose any term, we can just find that all of the terms like L0x, if it is written, so it can be written in the form of like x minus x1 to x minus xn divided by like x0 minus x1 to x0 minus xn here. So, if we want to add extra more term or one more term there, then we have to do all of the computations again. So, that is why we can just go for like Newton's divided difference interpolation formula for the better computation, or it requires like less computation for an extra addition of these points here. Thank you for listening this lecture.